So, dear colleagues and friends, good morning, everybody in presence and online. Well, I'm happy that at least some of you made it at the last day of the ICRA here to be in the workshop. On behalf of our organizers, Rini Zhao, Oliver Brock, Koichi Sutsumori, Helge Würdemann, Jan Peters, and myself, I would like to welcome you officially. My name is Annika Rath. I'm a full professor in Hanover, Leibniz University, Germany. It's this intersection of Berlin and Hamburg, if you don't know Germany. And I'm heading the Institute of Assembly Technology. As part of this, I'm a spokesperson for a quite large joint project, the Priority Program, which we'll see on the next slide. It sounds soft material robotic systems. The project is funded by the German Research Foundation. It's about 26 principal investigators, 30 doctoral students and research assistants. And we work together between different disciplines and 16 projects. It's funded about 6 years, and we are in the midterm now, and the overall amount is at around 12 million euros. We have researchers from very different disciplines, from mechanical engineers, electrical engineers, computer scientists, material scientists, and chemists working together. And the cooperation, especially with the material scientists and chemists, shows that we still have to learn from each other, what we can offer and what are the needs. And this is also one of the reasons why we initiated this workshop. And I hope we will get a little bit deeper into our disciplines and share knowledge and increase the cooperation. And with this short introduction, I would like now to start this workshop. And I'm very happy and pleased that we have been able to attract so many prestigious and excellent researchers and speakers for our workshop. And with this small introduction, I would like to welcome our first speaker and workshop organizer, Koichi Sutsumori, and I'm looking forward to his opening lecture.
Thank you very much for the introduction. Okay, hello everyone. I'm Koichi Sutsumori, Tokyo Tech, and I'm sorry I don't participate in person. And originally I have planned to talk about untethered pneumatics, but as an opening talk, I'd like to make a more general talk on soft robot and material science. And I believe materials are the most important key technology to develop new soft robots. And I will talk my expectations to material science from the viewpoint of soft robotics. And first, let me talk about soft robot project in Japan. A big research project started in 2018, and I'm a manager of this project. And these are symbolic images of the goal of our project. And this slide shows a background concept of this project. I believe conventional robotics is based on the value of conventional engineering, that is speed, force, accuracy, and certainty. This results in great success in industries, as you know, but I'm afraid that the current robots still cannot realize some performances in our daily life, which living creature can do easily. For example, it's not easy for today's robots to hang a baby with gentle touch. Soft robotics can be said a new robotics based on the values of biological systems such as flexibility, adaptability, and ikagen. And ikagen is a Japanese word which means accepting ambiguity and uncertainty and using them in an appropriate manner. And many new researches on softness have been born recently in various fields such as mechatronics, material science, and computer science. And the interesting point is that these technologies are bad technology from the viewpoint of conventional robotics. Robot arm, which is easily deformed by the external load, is a bad mechanical design in conventional robotics. These materials are fragile and unstable, bad materials. And recent AI returns different answer each time. They can be said unstable technology. However, they actually work well. Applying these soft technology to robotics will create a new academic discipline, soft robotics. That is my basic idea on my project. So this is the outline of the project. MEXT stands for Ministry of Education and Science in Japan. And the project term is 5 years. The budget is 1.2 billion Japanese yen, or about 10 million US dollars. Many researchers are working in this project, gathering from various fields such as mechatronics, material science, computer science, and biology and zoology. Totally about 150 researchers and students are working in this project. These are examples of the research in this project related to material science. This is a self-moving gel in which chained chemical reaction occurs and the gel moves by itself. This is my work, polymer actuators, which includes IPMC actuator and DEA. And this is a flexible electronics, including sensor and solar battery. And this is a biological materials aiming self-organization. And we are working also with industries to apply our results to practical use. These are examples, and some of them are already commercialized. Next, I will show two examples of my research related to material science. This is a research for untethered pneumatic actuator. Pneumatic is a very good actuator, but it has big problem, as you know, that's air supply hoses. I believe tetherless, untethered pneumatics would greatly expand the application of pneumatic actuators. So we are trying reversible gas liquid phase change chemical reaction, that's the electrolysis and synthesis of water. We use proton exchange membrane, PEM, and control the reaction by electrical current. Applying the current generate oxygen gas and hydrogen gas from water, and increasing the volume and the pressure. When we shorten the electrodes or connect them to an empty capacitor, the gases return to water, and volume and pressure is decreased. And the important point is that this works as a fuel cell during the gas absorption process. This means that we can recover the energy to make efficient driving. You can see here the chemical reaction on this movie. This is a hydrogen gas side, and this is oxygen gas side, and this is in the real-time movie, and we can control the gas generation of the absorption by the current. This prototype has a pen inside in a water-filled rubber bag. Applying the current generates gases and the rubber bag expands. While when the electrodes are shortened, the rubber bag returns to the original shape. You can see the movie on this motion on this movie. Okay. This is hydrogen gas, and this is water, and this is a real-time movie, and this is oxygen gas, and this is water, and the rubber bag is transparent, so you can see the expansion and shrink of the rubber bag, and we can control the rubber bag deformation by current. This shows example of experimental result of pressure control. This is a pressure, and this is a electrical current. During the period A, the current is applied to the device from battery, and the gases are generated from water, increasing the pressure. And during the period B, switch between the battery and the device is open, and the current is zero, and pressure is almost kept constant. And when we shorten the electrodes during the C, the current generated in the reverse direction, and the gases return to the water. This is the first prototype, our first prototype of hose-free pneumatic robot. No needs of air supply hose. These are pneumatic bellow-type rubber arms, and it has PEM inside, which is driven by this battery, and control circuit. The circuit has a wireless communication function. So this robot is totally untethered, perfectly untethered pneumatic robot. This shows the inside. This is a PEM. This is a PEM here, and this is a water. And applying the current generates the gases and arm bent. And this is a gas absorption process. The gases return to the water, and pressure decrease, and arm return to the original shape. We have applied this mechanism to Makime muscle. We fabricate the soft PEM tube and insert it to the Makime muscle. This is a PEM tube, and this is a muscle, which is filled with water. And you can see the motion. It has several problems now. Speed is slow, and durability is not good. The reason is mainly the bad electrodes on the PEM tube. So we are trying to improve now. This is another example. This is our very recent work, just presented on the day before yesterday in this ICRA. We are working with giraffe anatomist and developing a giraffe robot. A giraffe neck is a typical example in nature which shows flexibility and also power, which consists of various types of soft materials, such as muscle, of course, ligament and disc, and fascia and fat. So soft materials with various properties are very important to realize soft robot bodies. Next, I will talk about the material science from the viewpoint of soft robotics. This slide shows materials and functions in rigid robot, soft robot, biorobot, and living creature. I think one of the final goals of soft robotics might be living creature. Rigid robot consists of rigid and stable materials such as metal and plastics, which result in power and accuracy. A soft robot consists of soft materials such as elastomer, polymer, and gel, which result in the adaptability and flexibility. And biorobots consist of cell and living tissues, resulting in self-repair and adaptability. And living creatures consist of cells, protein, DNA, resulting in growing and evolution. As shown here, softer materials result in robot with higher adaptability and flexibility. And generally, main functional features of robot are body, motion, and intelligence. I expect active materials realize a new motion, intelligent material realize new intelligence, and self-organizing material realize new body. For example, I expect active materials realizing soft actuators and elastic mechanisms, and intelligent materials realizing flexible sensors and physical data processing, and self-organizing materials realizing self-repair and growing bodies. One of my big expectations to material science in future is in self-organizing materials. I believe that they have a great potential in soft robotics. Nature can easily fabricate a body with a self-organizing process, while current robots are fabricated one by one. If robotics can use a self-organizing materials or self-assembling process, I believe many novel functions will be realized. For example, new functions based on integrated microstructures, self-repair, and growing. Okay, this is a dream that robot research had since long ago. This is from the 1980s. That is a robot creates his child, and child creates his child. At current, robot can make robot, but it can't make grandchild. If we get self-organizing materials and fabrication technique, I believe the concept of robots will be drastically changed, and I expect interdisciplinary works with material science and soft robots could realize this kind of big dream. Okay, thank you very much for your attention. Thank you very much.
Do we have any questions?
Thank you very much. I very much enjoyed your research on the untethered actuation system that you presented in the first part of your talk. I was wondering if you have investigated how often you can repeat the cycle of actuation and how the performance will look like.
You mean the speed or durability?
The repeatability and the actuation speed.
Okay. Yes, I'm afraid the research is still experimental stage, and we need to improve. But durability, first speed, and if the point is quality of electrodes. So if we can get, for example, first plate type PEM, it's a very quality of electrodes are very nice, and it realizes 1 hertz motion, about 1 hertz motion. And but for example, in my talk, I show the PEM tube. So fabricating the electrodes inside the tube is very difficult. So quality of the electrodes, the tube is bad. So the speed is very bad at now. About 30 minutes to one motion. So it depends on the quality of electrode. And also about the durability. It's the same way. The plate type PEM works very well, and I believe that about 1,000 or more it works without problem. But about talking about the PEM tube, it's very bad. 10 times or 10 times working. After 10 times working, motion is decreased very much.
I have a more general question. When you started your work, your pioneering work, but also the current work, what was your idea to choose the proper material? Do you get these experience or the knowledge of the material for yourself, or was it a cooperation with material scientists what let you choose the kind of material you used for your robots or your actuation systems?
So we had been working with very many material scientists in mainly polymer material scientists, and some of them are functional materials, and I'm now interested. At first, I interested in just I'm looking for the industrial material with a very good elasticity. But at current, I'm very interested in the self-organizing materials. And I'm planning to start the next project for the self-organized materials, working with chemists.
For your vision, for your self-organizing material, you already have some cooperations, some material scientists who do this in this direction?
Yes, understanding each other is most important. So at first, they don't understand what I say. And also, I don't understand why they are not interested in. The topics which interested in is sometimes not interesting for the material scientists. So having a common target is the most important.
Yeah, hi everyone. I'm very happy that so many people showed up. I mean, to the people online, there are more people sitting in this room that you can't see on the video capture. I'm happy that so many people, that so many speakers agreed to talk here at our workshop. I'm really looking forward to that. I hope I wasn't too annoying with all my emails that I sent in the last weeks. It was a lot of organization back and forth. Yeah, but I'm really looking forward to this day. I hope with our technique here we get better throughout the day. It's a learning process. We have a lot of laptops and the capture card and whatever connected here. And yeah, so let me give you a short overview of what we have today here. After this great and inspiring opening talk, we will now have a session with Sabine Ludwigs, Renee Zhao, Barbara Mazzolai, and Ingrid Graz. After a short break, we will then continue with a featured talk by Carmen Mayidi and our contributed papers. Thank you very much to the authors that submitted great extended abstracts, and we'll have a poster session outside where we can discuss that more in detail. And yeah, after the lunch break, we will then have the next session, starting with Rebecca Kramer-Botiglio, Jonathan Rossiter, Alison Okamura, and Adam Stokes. And after another little bit shorter break, we will come to the last session with Robert Shepard and Sheila Russo, and our panel discussion in the end, moderated by Laura Blumenschein. Thank you very much already for that, for this cooperation. So yeah, let's get started with our first speaker of this session, Sabine Ludwigs. Yeah, I can see you and I think we can hear you.